Hello everyone, my name is Nasim Tavakoli, and today I will talk about how hyperuniform nanostructuring can trap the light into ultrathin silicon, either in a single junction or in tandem devices. This work is a collaboration between 3D Photovoltaics Group at AMOLF and a group of Professor Kundering, Ricardo Sapienza, and Marian Floresco. I would like to thank all of them and also my other colleagues that you can see here who have contributed to this project. I would like to start with the motivation of the work and tell you about why going to ultra-thin would be beneficial. The important reason to go for ultra-thin silicon is flexibility and cost. In the cost argument, I would like to show this plot from a techno-economical paper that I have found, that only by going to lower thicknesses, the module cost going down a lot. You might think silicon is already cheap and that is not that important, but in large scale, that's actually very beneficial. The challenges that we find is the surface passivation and light trapping. Surface passivation is very relevant in the case of ultra-thin solar cells because of the surface recombination that we will have in the backside of the PV. The good news is that in the state-of-the-art PV, that problem has been solved to a really good extent, and we have really good surface passivation now. In the argument of light trapping, I would like to show you that when we go for, in different kinds of silicon, when we go thinner, you can see that the efficiency of the module is actually going high because of having less recombination in the bulk. But from a certain point on, this trend is changing, and that is because how silicon is not a good absorber, especially for the red and near-infrared photons. Light trapping would be tackling that problem, and that is what I'm going to focus on in this talk. The disordered honeycomb structure here is what I'm introducing as this solution for that problem. This structure is optimized to trap the light into silicon 1 micron. You can see the etching is for 200 nanometers for silicon 1 micron, and we also have anti-reflection coating. So we have fabricated these structures on silicon 1 micron that you can see in the middle side. You can see that's kind of transparent. You can also see the darker areas that these structures have been fabricated on. Here you have a SCM image of the structures that we fabricated. In the next step, we did absorption measurement using an integrating sphere on both areas with the structures and without the structures to compare them. Here in the solid lines, you can see what we expect to see from theory, and in dotted line, you have what experimentally has been measured. As you can see, when we have the structures, the absorption is increased quite a lot, especially in the range that silicon is not a good absorber. You can see that for the case of measurement, the integrated absorption goes high from 24% into 66%, which is a really nice increase in absorption. But how does this work? To tell you about that, I would like to start with silicon film without any structure on top. And what happens when light shines into this structure is that a part of the light will go through the thin film silicon, will be absorbed there, but there are a big part of the light that will escape from either side of the film. Now imagine we introduce these structures on top, and now we can diffract the light into different angles. As you can see, for some of these angles, still we lose the light because this is where the light is escaping. But there is a range of angles, as you can see here in solid lines, that in this range of angles, the light will be totally reflected inside the silicon film because of the high refractive index, and we will increase the optical path of the light, and the absorption will be higher. If we look at the K space, we can see the K parallel as the interesting range of the K parallel as a ring in K space. In this plot, you can see for different wavelengths, these are the range of angles that are interesting for us, the range of K space. So what this hyperuniform structuring does for us is actually engineering the diffraction in K space to trap the light inside 1 micron silicon in this case. But what is hyperuniform? When I talk about hyperuniformity, what do I mean by that? To explain, I would like to start with this field of dots and these rings that we toss into this field of dots, and then we count the number of dots that fall into these rings. You can see that when we have an ordered lattice, for small rings, the number of dots are quite the same. Also, for bigger rings, they are not that different from each other. Here I show that this is the K space that all of you know that this is what we expect from an ordered lattice. So now if we introduce some kind of disorder to this ordered lattice, we can see that for small rings, the number of the dots inside the ring changes. But when we go to big enough rings, the numbers are actually not that different anymore. And that is because there is a kind of uniformity in this disorder that we have. And that is that for big enough areas, the density is kind of uniform. And this is how we can control the diffraction pattern. So because we don't have two dots very far from each other, we avoid having diffracted light into this central part. Of course, that's not the case for a random distribution. And as you can see, by going to bigger rings, we actually have a huge difference in the number of dots inside these rings. And that actually brings us to this kind of light diffracted into all different angles in these cases. So the mathematical definition of hyperuniformity is that when for large areas, the number variance within an area of radius r grows more slowly than the area. And this is how these two ordered lattice and disordered hyperuniform falls into this definition, but definitely not the random distribution. So now that we know what is hyperuniformity, let's go back to the structure that we made. And now we want to measure the Fourier space to see if we can actually see these rings in the K space. So for this structure, this is what we expect from theory. And then we measure the K space using a Fourier microscope. And as you can see here, the measurement, the ring that we see in the measurements agrees quite well with what we expect from theory. In this plot, we have plotted the radial distribution, and you can see that from theory and measurement, they agree quite well. We also fabricated other disordered hyperuniform designs. And also for those cases, we see that these rings are quite similar to what we expect to see. We also measured the absorption, of course. In theory, in the left side, in theory, as we can see, we expect that all of the hyperuniform structures, they have very similar light trapping properties. And in the right side, which is experiment, you can see that that's again, it's the case that the absorption is increased quite a lot by introducing these structures. Although you might think, what is with the whole structure, the lower structure, that we see it doesn't perform as well as the other ones. And I would have to tell you that is a mistake that we made in the conversion of the files between theory and fabrication. And that is why this is not actually the optimized structure that we fabricated. So the next step for us was to estimate the photovoltaic efficiency. In this case, we wanted to have also a back reflector, a perfect metal in the back. So that is why we are using the theory data from now on. So to get the photovoltaic efficiency estimation, we need a couple of numbers. Photocurrent is one of them, and that number now is calculated by using the absorption data. As you can see here, in the case of flat, we start with 18.5 milliampere centimeter squared, and in the best case, we get as high as 34.8 milliampere centimeter squared, which is really nice. The next number that we need is the open circuit voltage. Papine has done a really good job of a realistic modeling of these structures on a kind of state-of-the-art photovoltaics. So he used numbers for carrier lifetime, doping concentration profile, surface passivation, for the state-of-the-art PV, and then he calculated that, what is the how much extra surface area we have by introducing these structures. So that is also what he took into account, and he calculated these numbers for open circuit voltage. And as you can see, we expect to have lower open circuit voltage because of extra surface that we have, but that is nicely compensated by the really good absorption, which leads to short circuit current. Next step is to get the full IV curve and get the efficiency under one sun illumination. As you can see, the efficiency for the flat case is 12%, but in the best case, we can reach to almost 23%, which is amazing. To put these numbers into perspective, I also put the highest efficiency in year 2019 for other types of thin film solar cells, CIGS and cadmium telluride, and you can see the numbers are similar. Although we are using silicon, which is cheap and is not toxic. I also have put organic cells record efficiency because in the argument of flexibility, I thought that is relevant. And as you can see, the number is not that high. Another thing that we would like to look at when we introduce a structuring for solar cell fabrication is if large-scale fabrication is possible. I would like to show you two works here. One of them is this beautiful work that they use ionic strength of the colloidal dispersion solution that they have, and they can control the interparticle spacing. So the PMMA beads that are used here, you can see in this sample here, the interparticle spacing is quite similar. So this really looks like a disordered hyperuniform structure that I showed you before. And indeed, when they did optical measurement, this ringing K space is what can be seen. So this sample has been made for areas up to 15 by 20 centimeters square, which shows us that it can be made in large scale. This fabricated substrate now can be used as a template for etching or nanosphere lithography, or it can be overcoated with optical materials. Also, Merlinda in our group, she managed to get from electrochemical growth she managed to get this indium network by self-assembly of indium particles. She's still working to fine-tune this, but what I'm trying to say is that we are moving into that direction. I would like to go for a recap now before moving to the second part of my presentation. So what I have shown you so far is that there are different disordered hyperuniform designs that can be used for increasing the absorption in ultrathin silicon. So we have seen this ring in K-space, which is the range of angles that the light will be trapped in. We measured the experimental absorption, and we could see that that's actually the case. And we looked at device performance and how much it can be improved, and that's actually quite a lot of improvement from 12% to almost 23%. And that is really good. So now I would like to move to the second part of my presentation, which is about tandem solar cells. And that is when we have more than one material. So a combination of different materials with different band gaps. I would like to go to tell you why is that beneficial, and then explain more about the design that we have. So the advantages of the tandem solar cell is that we reduce thermalization loss in PV conversion, and that increases efficiency. And thermalization loss is this part of the energy that is lost for high energy photons, which we cannot make use of when we have only one material. In principle, when we add more materials, we would have way less of this thermalization. So the materials that I use is silicon as a bottom cell because it's a really good PV material, and it has very mature fabrication technologies. And as a top cell, I would like to use a 3,5 material, and they are also really common in PV. They have high absorption coefficient, and they have really good light matter interaction. The challenges. One challenge is that when we use 3,5 material on top, all the high energy photons will be absorbed in that material as a top cell, and silicon would be responsible to absorb the near infrared photons. As you know, silicon is a poor absorber in that range, and that is what we already talked about. The other problem is that 3,5 materials cannot be grown on silicon without having a lot of defects. And that is why we came up with this design, which tackles both of these problems. Gallium arsenide nanowires are possible to be grown on silicon without having a lot of defects, and that work has been done before. Also, if we have an array of nanowires, this can be used as a grating to increase the light absorption in silicon in a similar manner that we saw in the first part of my talk. So let's see in calculation and simulation if that's actually the case. So I'm going to look at the absorption into silicon bottom cell to see if by adding nanowires on top, I can increase the absorption in the near infrared part or not. So here I am showing you the near infrared part of the spectrum, and the dashed line is the light absorption in the case of having no nanowire array on top, and the spiky solid line is the absorption in silicon when we have the gallium arsenide nanowires on top. This is a really good improvement. We can see that from the short circuit current of 0.9 milliampere square centimeter, we get to 2.9, and that is a really good increase. Also, if we look at the direction of the light inside silicon, we can see this kind of diffraction pattern, and exactly at the angles that we expect them to see, expect to see them from grating equation. So that actually shows that the principle that we talked about, the light trapping that we talked about in the first part, it actually can be used for tandem solar cells as well. You would think the shape of the absorption is quite different in these two cases, and you might wonder if these spikes are actually real data or it can be an error or something. I'm going to explain these sharp peaks by showing you the wave guiding modes of the two cases of 1 micron silicon in the left side and 2 micron silicon in the right side. Note that we have the full range of wavelength in the right side because we have only one material, silicon. And in the right side, we are only looking at the near infrared part. So wave guiding modes, they show that for each wavelength, what is the K-parallel needed for the light to enter the material to be trapped, to be coupled to these modes. In the case of a hyperuniform, we have this ring in the K-space, which introduces this band in K-parallel, as you can see here. And this band overlaps with all of these lines, which results in a smooth increase in absorption. In the case of an array, these K-parallels are specific diffraction orders, and that can be shown as these particular lines that can be crossed with the wave guiding modes at particular places. And this is why we see these spikes in the case of an array, and we see this smooth increase in the case of a hyperuniform. I would also like to show you that if you look at the field profile of this design from the side we are looking here now, these are the nanowires from the side that you can see. This is the array, and this is the silicon bottom cell that we see here. And we are looking at two of these spikes, these peaks, and the area in between. As you can see, we can see the profile of wave-guided modes of TE and TM with a fixed number of nodes, and that is what we expect. Last thing I would like to talk to you about is the conversion efficiency. So I have done the simulations for the absorption of the nanowire array on top of silicon for different periodicity. Here you can see different periodicity of the nanowires, and also for different diameters, which results to different filling fraction for gallium arsenide. The best efficiency that we get is 33%, and this is not even an optimized design. So I would like to compare this number with the case of not having nanowires and having nanowires. And what I want to point out is that when we have a full area covered, gallium arsenide covered, gallium arsenide efficiency is more than 32%, but silicon doesn't absorb at all, and the efficiency is really low. In the case of having nanowires, the efficiency of the gallium arsenide is slightly lower, but we can see that we have a really good increase in silicon bottom cell. So a proof of principle that we wanted to show that by using this grating, we can use the same principle to increase the efficiency of silicon bottom cell is actually proved. With that, I would like to go to a conclusion of my talk. I hope I could convince you that that by using the hyperuniform designs, we can have a really good ultra-thin silicon solar cells. And this concept can be used both for single junction solar cells and for tandem solar cells. With that, I would like to thank you for your attention. Please, if you have any question, write an email to me to n.tavakoli@amuf.nl. And I wish you a good day and enjoy the rest of the conference. Thank you.